We talked about that KEQ last time, and then we did a delta G calculation just to prove that no matter how we do it, we basically get the same number. Let's go ahead now and look at the following. Oh, get some glasses on so I can do this right. All right, so I have a neat little example. I'm going to have AgCl solid, going to make Ag plus and Cl minus. Now, what I'm going to do is I'm going to go ahead and get some data for us. So from the CRC, I'm going to get delta H naught and S naught. So I'm just going to go ahead and look these two things up. For silver chloride, the delta H naught is negative 30.97. And this one happened to be in kcals per mole. So let me note that. The silver ion was 25.234, and the chloride is negative 39.952. The S naught, this one's going to be in calories per mole Kelvin. The S naught is going to be, I love these, this is great. Seems silly, but 23. Everything else has all these decimals, and then you go like, oh, 23. 17.37 and 13.5. Now, since I did these guys in calories, because that's what I read, I should note that 1 calorie is equal to...
Is that negative 36 or negative 30?
You're talking about this one?
Yeah.
That is negative 30. So 1 calorie is 4.186 joules. So that way we can get this all back to joules here a little bit later if we need. What I want us to do is go ahead and get some delta G and then take it one step further. So we're going to do this calculation just like we normally would. Let's get our delta H naught. So that's the products minus the reactants. So that's 25.234 plus the negative 39. So I'm just going to go minus. Is that okay? Or do you want me to say plus the negative?
I would go ahead and do plus the negative.
Okay. Man, if I could write a plus sign. Plus the negative 39.952. That's the products minus the reactants is a negative 30.37. And these are all in kcal per mole. So if you do this, you know, as I keep saying, it's just math. We're just plugging and chugging at this point. We get 15652 kcal per mole. We'll go ahead and get that 1 calorie is 4.186 joules. And at the end, that will get us, so I just want to double check my number on that one.
Getting 65.5.
Okay, that's what I had too. I just know that I had a slightly different number in my notes, so I just want to make sure that the one I have in my notes is the correct one. Okay, so if this is the delta H naught, it is 65.5. Ben, what does that tell you?
Gaining energy?
Right, it's endothermic. So enthalpically, is this favorable or not?
Yes.
Not favorable. Now, the reason why it's not favorable, Dallas, is because enthalpically it says, look, if you want me to do this, you are going to have to pump a bunch of energy into me. I'm not going to give it off. You're going to have to make me do it. Remember, Mother Nature wants to minimize her energy as much as possible. So if the bond energy after is more than the bond energy before, we are going to have to do something to make that happen.
Hey, quick question. You don't worry about the kcals? You don't worry about the kilo?
Oh, so what do you mean? Oh, I think I see what you're saying. Take a look. All we canceled out was a cal.
Oh, okay.
So we have a KJ.
Gotcha.
Yeah. Okay. Yeah, that conversion actually is we could have gone about it a long way around insofar as we could have said kilocalories to calories, calories to joules, joules back to kcalories, or kilojoules, sorry. But since we're technically only getting rid of the cal part, we can keep the K part. All right, so let's do delta S naught. And that is going to be, I can't trust those, so 17.37, I believe, plus 13.5 minus 23. And this is again calories per mole Kelvin. Do that, you get, what is that, 7.87? Dallas, confirm.
Yeah, that's what I'm getting.
Thank you. I'm in the process of rewriting some of these notes because if nothing else, they've been smudged over time, so it's kind of hard to read some of the things. And then we're going to do 4.184 joules is 1 calorie. And so my old number, Dallas, was, sorry, 86, sorry, thank you. I don't know why I keep doing that, like this calculus slip. It bothers me. I'm a freaking chemical engineer, for Pete's sake. I knew that thing like the back of my hand, and yet every single time I do that.
32.9.
32.9, thank you. 32.9 joules per mole Kelvin. So what does that mean? That means disordered. Now, this is kind of where it gets fun.
Wait a minute. So that means that entropically
Entropy.
it does want to go?
Right. Sorry, I should have written that down. Right. Disordered. Favorable. Again, you can have these competitive effects, Dallas,
Wait,
It's okay.
I just want to clarify. So for the S, a positive number is favorable. For the H, a negative is favorable.
And for a G, negative is favorable. Welcome
Okay.
to the wonderful mind of positives and negatives. And again, man, you're going to get in physics, you're going to be positive and negativing these things left and right, depending on your frame of reference and your point of reference, not even just frame of your point of reference. We made zero entropy at 0 Kelvin. It can only get more disordered from there. And we all know that Mother Nature likes chaos. So yeah, that's positive. But we defined losing energy as the favorable direction for creating and forming bonds. So because of that, you end up having to keep in your mind which one is the way it wants to go. And it's not always, positive is not always the thing you want. And I know it gets kind of weird. So in fact, we may get to that later today when we talk about oxidation and reduction. I will really blow your mind because if you're being oxidized, you are a reducing agent. And if you're being reduced, you're an oxidizing agent. That gets really kind of interesting. So I digress or accidentally go forward. Let's get delta G, is going to be delta H naught minus T delta S naught. And so that is 65.5 kilojoules per mole minus 298 Kelvin times 0.0329 kilojoules mole Kelvin. Okay. So again, I want to point out, Dallas, and this is something that I'm sure I always fall into, so I'm sure there's plenty of you that are falling into it. We see these numbers of 65 and 33, and we go like, wow, those are like almost exactly the same number. So they're going to really like almost cancel each other out, right? Nothing's going to happen. Not so. The 65.5 is a kilojoule. This guy's only a joule. So that's why we pay attention. Units matter, and we got to watch them. So they aren't the same number, which is why that guy gets turned into a 0329. So just be careful with that, guys. That's actually one of the bigger mistakes that people make, is to not turn that into the kilojoules, keep them in the same. And we do want it in kilojoules because otherwise the numbers just get stupid. All right. So in this, what's that calculation?
I
55.
get 55.7.
55.7 kilojoules per mole. And I'm going to go ahead and just say that that's 55700 joules per mole, just to keep that there for a second. Okay, and that's a positive number. So let me just make sure that we all know that that's a positive number. So what does this tell us? Low band. What does a positive delta G tell us?
Didn't you just say it's unfavorable?
Yeah. Not gonna happen. Now, can somebody finish that statement though? Leilani Singh.
It means it's disordered or not disordered.
Well, it wants to go to disorder.
Mm-hmm.
Kyra, what's the rest of my statement that I'm going to say? This is not going to happen.
It's not spontaneous.
Okay,
On its own.
close. Look back in your notes. I was very explicit about this. Not spontaneous.
Let's see.
Let me just rewrite it down here. Not going to happen. Not spontaneous
As written?
as written. So what does that mean?
The other direction is.
Yes. It is going backward. That is a spontaneous direction. All right. Now, what's really interesting about this problem, and I love this problem, because one, we have to start thinking about the competitive effects between enthalpic and entropic contributions to Gibbs. The other is, we as in the class, we always start this problem right up here, and we're like, okay, so we have this thing, and we got numbers and blah, 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 math, whatever. Okay, we think a little bit here on the blue stuff, whatever. Okay, we get a thing. But we never stopped to think about that equation right there. Silver chloride breaking apart, making an equilibrium to silver and chlorine. So what we need to do is we need to actually use all the tools in our toolbox. So why am I making you think about this? Patrick, tell me what that equation is telling you. Everything you know. Be as blasé as possible, and we'll try to drill down. You start the ball rolling. Patrick, press your space bar and talk to me. Oh, look at the defiance.
My microphone wasn't plugged in. What were you asking again? Sorry.
I want you to take a look at that AgCl breaking apart to Ag pluses and Cl minuses. Tell me everything that you know about this system. Yeah, and you can be as obvious as possible. Just start the ball rolling.
Gosh, cannot
You're
think.
thinking about it too hard.
Yeah, I am.
Please just say silver chloride is breaking up into its ions.
Yeah, it's breaking into its ions.
Okay, good. What else do we know about that system? We did an experiment about this.
It's in water.
Okay, it's in water. What else?
We know that chlorine normally likes to break apart.
Uh-huh. What do we know about silver?
Transition metal.
Fair enough.
It's
Go back
not
to your solubility field. It is not soluble. That is correct. Now, we know that the silver does not like to dissolve. We are asking it to dissolve. And it says no. So this number makes sense. This Gibbs free energy is saying like, hey, do you want to go or not? Says, no, I am not going to do it as you wrote that thing to do. What would I rather do? I would rather grab those chlorines and go backward and make the solid. And that makes sense. This makes sense. Why? Kyra says, silver is not soluble. Check. All right, that's one thing. Ben tells me about the knot. What does that mean?
Initial.
No. When I say delta H naught, what does that mean?
1 mole.
1 mole. 1 molar. 25 degrees Celsius. 1 atmosphere. Now, of course, the pressure doesn't matter here. We're not talking about a gas, so we don't care about that. But this is what we're talking about. We're talking about putting 1 molar's worth of stuff into solution and expecting it to continue to break apart. That's not going to happen. We put 1 molar Ag plus, 1 molar Cl minus into the container. And still expect AgCl to break up. No way. We know that silver is insoluble. Silver is not soluble, so if I put a whole bunch in, why am I going to continue to break apart?
Well, I mean, obviously the end result is no, it won't. But
Yep, so what's this?
the theory would be that, like the hypothesis would be, oh, that chlorine wanting to break apart would overpower that. Evidently, that ends up not being the case.
Yeah, of course. Right, this is where I keep getting you there, is it's a competitive effect. Now, delta G naught is equal to delta H naught minus T delta S naught, but we also had delta G naught is equal to negative RT natural log of KEQ. Rearrange this. KEQ is equal to E to the negative delta G naught over RT. So that is E to the negative 55700 joules per mole over the 8.314, whoa, 8.314 joules per mole Kelvin. And since we're at the naught, we're at 298 Kelvin. KEQ, what'd you calculate there, Dallas? Because I have a slightly different number in mine up there. Let's see.
I have 1.74 times 10 to the negative 10.
1.74 times 10 to the negative 10. Now, I can't remember when we started this. So I'm just going to go back in my notes here real quick. First, I'm going to let you guys catch up. Now, first of all, we do have 1.74 times 10 to the minus 10, right? This is a small KEQ, which means very little product. Which means concentrations of Ag plus, Cl minus cannot be 1 molar. So they go backward. Le Chatelier. We loaded up the products. It didn't want to be there. They went back to the reactants, as we expect. Now, I'm going to go back in the notes here real quick, just in case. Well, we may have already done that. All right, I can't. Who takes good notes here? I want you to go back to when we talked about the KSPs and we were doing those calculations. Somebody go back and tell me, what did I tell you the KSP for silver chloride was? Somebody flip back in their notes.
1.8 and
Yep. Right. So what have we just done? This is probably one of my more favorite parts.
Created a rounding error.
Say it again.
Created a rounding error.
Sure, that's not what I'm asking or trying to point out though, Dallas. Yes, of course, there's always experimental errors there, or maybe someone has a number just slightly off. That's not the point. The point is that we started this conversation about equilibria about, I don't know, 6-7 weeks ago or something like that. And one of the things we said is, hey, these people have measured these values and they can figure out how much of their product they're going to make. And we just sort of accepted it. And then we come to the idea of, well, are you going to go in the first place? Are you going to actually make what we're asking you to make? And so we go through thermodynamic data and we either look up our delta H's or S's, or we could sometimes look up delta G's directly. In this case, we had to calculate it. But at the end of the day, our delta G said, hey, if you want this reaction right here to occur, if you want that to break apart, delta G says, no, I'm not. Well, delta G not, I should say. So when the delta G naught is being calculated, we have to understand that that is actually doing it at a 1 molar situation. Well, we can go the way back machine to intro chem when we went over solubility rules, or even in Chem 120 when we did them. And we can look at that and say, well, silver's not soluble anyway, so of course it's not going to do what we want to do. But what does that also mean? That the thermodynamic data can be related back to the equilibrium constant. And that equilibrium constant, is the same one I gave you 6 or 7 weeks ago. This right here is one of the more powerful things because it links that qualitative idea of which way will a reaction go and what happens if you load up a reactant side or load up a product side or take away from something, and it will shift accordingly. It'll shift because of the thermodynamics involved. If you want that reaction to actually go the direction you want it to go, if you want silver chloride to break up, however little it will, then you got to make sure that you are nowhere near this 1 molar conditions. You're going to have to be with like no ions in solution. You still won't get very many, but at least you'll get some of the silver chloride to break apart. You know, like 1/10,000th will break apart. But then you wouldn't be talking about a delta G naught. You'd be talking about a delta G.
So so does that mean that at the concentrations and stuff such that, you know, it does break apart and whatnot, we do have some of it breaking apart, is the delta G different, you know?
Yeah. So okay. So remember, we've been doing a lot of delta G naughts, right?
Yeah.
So what you're saying is, Dallas asks, so if AgCl were in pure water, right?
Yep.
it would break up a little, right?
Yep.
Well, remember, that's delta G equals delta G naught plus RT ln Q. So what you do is you figure out just what is the delta G naught, and then how far away do we have to be such that this unfavorable, so this is not favorable, and this is yes favorable, if the Q, or if the RT ln Q overrides delta G naught. So what you have to do is you got to figure out what value of that Q, how much do you have to take the products down such that you can actually get that quantity to override the not favorable delta G naught. And it can be done, and you can do it. So I have something perhaps in that same vein for you, Dallas.
Yeah.
Can any work be done by dilution? So you're going to take something concentrated and dilute it down. Can you actually get work out of that? What is the free energy? What is the free energy of diluting saturated NaCl to 1 molar NaCl? So what I've done is I've taken my salt, I have dumped it into a container until it can have no more. I'll go ahead and decant off that solution. So I just am left with the saturated solution, no solids left in the container at all. And now I want to go ahead and dilute it to 1 molar. What's the free energy of that? So, dump salt into water until it can hold no more. Decant the liquid. No more solid, so we don't have to worry about that anymore. Dilute to 1 molar. That's what we're going to do. So because we're going to do this in 2 steps, I want to look at those 2 steps. Step 1 is just getting solid salt to make NaCl that is saturated. And then I'm going to take this NaCl that is saturated, and this is a one-way trip now. I want to take it down to 1 molar NaCl. That is a horrible N over here. Hold on. Okay. So if I have two steps, then I have two delta G's. Watch this. I love this part. This is the Gibbs free energy of dilution. And you know what? I might be able to set this demo up at the end of this and show you. It may take me a minute. So the Gibbs free energy of dilution. All right. Time for some derivation. Yay! Okay, we have delta G is equal to delta G naught plus RT ln Q. Since I have two systems, I can compare delta G1 is equal to delta G1 naught plus RT natural log of Q1, and a delta G2 is equal to a delta G2 naught plus RT ln Q2. And overall, this will get us a delta G overall. Are you with me? I know as soon as I said it, everyone just like made a collective sigh and suddenly hated me a little bit.
One quick thing. So we have a delta G1 and a delta G2 equation, and we're saying that we can together they'll make a delta G overall. What is the equation that will connect those two?
Huh. Well, watch this.
Also, where does the energy come from?
Well, ask me that at the end.
Okay.
Let's do some math. Delta G2 minus delta G1. All right, so by the way, I should probably note this real quick. We'll just make this the saturated. Delta G1 will be the saturated. And G2 will be the dilute. So if I take 2 minus 1, that's going to get the overall, right? So let me actually, let me just move those guys over. So delta G overall is equal to delta G2 minus delta G1. And that's going to be delta G2 naught minus delta G1 naught plus RT natural log of Q2 minus natural log of Q1.
Forrest?
Yes.
I just don't really understand quite yet what any of this means because we haven't like.
Then don't understand yet. Don't understand yet. Follow. You'll see.
Okay.
Let me just point out. Solid salt. We're going to just dump a whole bunch in, stir, so no more can go in. Yes? Kimchi?
Yes.
Okay. We're going to pour some of that liquid off, leaving all the solid left in the former beaker so we don't worry about any more of this equilibrium to just create saturated NaCl.
But why is it saturated NaCl and not Na plus and Cl minus?
Oh, it is. I mean, when we write 1 molar NaCl, we're really saying 1 molar of Na pluses and 1 molar of Cl minuses swimming around.
Okay.
I mean, that's implied. You know, as soon as you have a liquidy solution, yes, it is those ions floating around. We just lump them together. right?
Yeah. I mean, I get what the steps are, but I just don't really get
Let me
the D is.
Yeah, let me finish the math. I'll try to set up a quick demo because I do
Okay.
have a voltmeter. I will show you that we get some voltage off of this, and then maybe that'll make sense. So just at this point, for once, Kimchi, just roll with it.
Okay.
All right. So we have our delta G equals delta G naught. So we're going to not be at standard conditions here. We're going to look for, because clearly we are not going to be at 1 molar. We just said we're going to saturate this thing. And I'll tell you what that means in a second. Actually, I could probably tell you right now. I probably should have put it up here. A saturated NaCl solution, this is going to be 6.11 molar, and we're going to go down to 1 molar. So the most saturated you can get NaCl is basically a 6 molar solution. After that, it all falls out. So what we're going to do, since we're not at anywhere close to like standard conditions, we are going to be talking about a delta G. And that delta G for both of them happens to be delta G naught plus RT ln Q. And that's the products over the reactants. Now our products happen to be those ions floating around versus the solid that was in solution. What I do want to point out here is, since delta G naught of 2 and 1 come from the same place, basically saturated conditions. They cancel out. Since the delta G naughts are going to be coming from saturated down to the 1 molar, these guys cancel each other out. And so what ends up happening is you see that the delta G overall is equal to RT natural log of Q2 over Q1. I can continue to write that as RT natural log of, this is going to get big, product 2 over reactant 2 over product 1 over reactant 1. Now, all I've done is followed some math. I subtracted out some stuff. I note that since the delta G naughts of both of these, because they are exactly the same system, their delta G naughts will have to be exactly the same. Okay? These guys, they cancel out. They are the same system. Oops. So I get rid of them. I simplify the delta G to be an RT ln Q2 over Q1. So remember, this is dilute over concentrated, right? So this is the dilute, that there's the concentrated. Now what I want us to take a look is at the expanded natural log, where I say product 2 over reactant 2 and product 1 over reactant 1. What are the reactants for basically making a concentrated solution? Come on, Dallas.
Of a concentrated solution?
Yeah. And what's the reactant to make my diluted system?
Wouldn't it be the
The
total number of
concentrated solution.
ions in the solution?
Well, yes, but what did I make the diluted thing from? I made it from the saturated solution. So reactant 1, oh, okay, I can write this a little bit better here. Reactant 1 and reactant 2 are both saturated solution. Their products are the ions. That's fine. The saturated condition is giving you the saturated amount of ions in solution. The dilute is saying, I started out with the saturated, but I'm going to go down to a lesser number of ions, a lesser number of products. So if that's the case, these two things go away. So now we're at RT, product 2 or product 1. Or, sorry, land. I forgot my land. Or RT, natural log. I'm just gonna write it down below. Or I'll just move it over actually. Or RT, natural log of dilute. Over concentrated. So for dilution, delta G is going to be RT natural log of your dilute solution over your concentrated. Now, I do want to point out that I have done this from a saturated condition itself, but I could have done it from, say, a 2 molar down to 1 molar. But again, to make the 2 molar, I have to start out with a saturated solution and dilute it down. To make the 1 molar, I have to start with a saturated solution and dilute it down. Therefore, both the concentrated and the dilute situations still come from that original saturated set of conditions. So all of that makes the delta G naughts go away. And because they all start from the same reactant, and that is 6.1 molar saturated conditions,
Okay.
the reactants for each of them go away. And we're just comparing one set of products, their concentration, to the other set. And so if we look at this, for us now, the delta G is equal to RT natural log of 1 molar over the 6.11 molar. Oh, so put in numbers, 8.314 joules per mole Kelvin. I'm going to go ahead and just choose the 298 Kelvin just because we're at room temperature. Natural log of 1 over 6.11. We don't need the units because natural logs won't have any units. And if you do that, you get negative 4.484 joules per mole. This will be interesting because I've never done this and I'm going to try this and see how it works. First of all, hopefully you guys realize what this means. The negative sign means,
Favorable.
huh?
Favorable.
Yep, it is spontaneous. You know, everything, if you think about it, you drop a drop of dye into water, it will dilute itself. It will spread itself out because the thermodynamics say, we're going to go. We're going to do this.
Is that because, oh, yeah.
Oh, yeah. No, go ahead, Kimchi.
Oh, okay. Is that because the negative is basically saying that it's releasing energy, which is like a good thing?
Yes.
Okay.
Now, that is the difference. I mean, you have to think about what you've done is dispersed out the distance between these ions. You have dispersed out how many water molecules can get around them, and those types of interactions. When we talk about bonds, we're also talking about actual interactions. So intermolecular forces counts as an energy. So as you disperse that energy, you are essentially lowering those bonds, lowering the energy of those bonds overall. Remember, you also have entropy at work here, right? A more dilute system has more degrees of freedom, has more places it can go, more places it can roam. So it's not just about the enthalpic thing of like, oh, because I mean, technically a solvent cage around each of these should all just sort of negate out. So this one would actually be entropically driven. So there you go, Dallas. Now we have an entropically driven one. Now, I do want to point out, diluting is spontaneous. This is how osmotic pressure works.
What's osmotic pressure?
Basically, what do they say? Water flows where salt goes, is what the bio people will say. If you have a salty side and a not salty side, the water will try to flow to the salty side. Now, they talk about a pressure because you have to separate that system. So you put a membrane there that only allows one direction of flow. And if something is moving through a membrane, something has to be driving that thing to go through the membrane, and it actually causes a pressure. And they call that osmotic pressure.
All right.
That's what I was wondering. Oh.
Right? I told you, Kimchi, I'm gonna
Well, that's what I was thinking of. Like when you asked, like, can work be done by dilution? You never asked us what we thought. And
No,
then you
because
just
I knew
started
you would know
going.
that. Kimchi, I knew you'd know that answer and you would steal my thunder. That's
Oh,
why.
okay.
Just too
But I
damn
didn't know if that was true. I was just asking if that's why that
But
happened.
no, but here's the funny thing. Here's the funny thing. The question is, how can you get that work to be done? And the fact of the matter is, as far as you and I might be concerned, it's ridiculously difficult, as far as I understand it, to take something from concentrated to dilute. I mean, from concentrated to dilute. But we actually do something like this all the time, right? If we recall this guy, desalination plants, what do they do?
I'm gonna go ahead and guess they desalinate things, i.e., remove the salt.
That's right. They remove salt from seawater to make fresh water. But what did we just say? We just, go ahead, Dallas.
That salt doesn't want to do that.
Yeah, right. We just proved that salt does not want to get more concentrated. We just proved that it is favorable to become dilute, not more concentrated. So in order to remove the salt from salt water, that means you basically have to say, all the salt, I want you to get into a smaller and smaller and smaller place so I can pull off more and more pure water. It takes a hell of a lot of energy to do it. That's why when some people go like, oh, if, you know, SoCal has such a problem with water and maybe we can like free up the Colorado River, just put some desalination plants, and like, well, you can. It just takes a tremendous amount of energy to basically shove that seawater back through the membrane, concentrate up the salt, and then somehow dispose of the salt, because you just can't keep it lying around. That'll be bad. But so this is why desalination plants are you know, not just popping up everywhere. They take a tremendous amount of energy to try to do this.
Wait, when you say desalination plant, do you mean plant as in like a power plant or like
Yes,
as in vegetable plant?
Power plant.
Okay.
Sorry. You know, I've just been in the communications studies hiring committee, and a couple people did demonstrations where they were talking about the contextual aspect of communication and how you may be thinking one thing while someone's thinking another. This is a classic example of this. He was thinking a physical plant and I was thinking manufacturing plant. That's funny.
Yeah.
Nice.
Hey, Forrest, I have a question.
No. Yes.
When can we use this equation?
Which one?
The simplified version.
This one?
Yeah, dilute over concentrated.
When you're seeing how much energy can be done by diluting. Or if you're if you're not comparing dissimilars, right? Because dissimilar, so if they were dissimilar systems, all of these values right here would have to be known and calculated, and you wouldn't be able to get rid of your reactants down here. You'd have to keep them all in there. You just have more things to keep track of. The reason why this is so nice is because it is all the same system and it all comes from the same place. There's a lot of simplification that can go on. So you could do this with dissimilar systems if you wanted. You just got to keep track of everything. But for dilution, you can skip straight to the end. You can use this equation you see in front of you and just go for it. Now, keep in mind, as I said, because any concentrated, not just saturated, but any concentrated solution comes from the saturated conditions, and any dilute system comes from the saturated conditions. Then we can compare them. I could instead, you know, just put a 1 molar and a 2 molar right here, right? I can put a 1 molar and a 2 molar. Dallas, will you put a 1 and a 2 there for me? Can you put a 1/2 in the natural log and just calculate it? I'll go ahead and just say.
It says negative 0.693147.
Damn it, Dallas. Negative 0.69 joules per mole.
Yeah, sorry,
Yeah.
the first answer it gave me was negative log of 2.
I don't understand that, but anyway. So you notice that the driving force here, if you're going from 2 molar to 1 molar, is not so good. It barely wants to do anything. You can barely get anything out of it. And that's to be expected. We're only cutting the stuff in half, but when you cut it by 6 times, that energy really starts moving. The more concentrated you are going to dilute, the more energy you're going to release. That seems to remind me of a safety thing that we all seem to know. Oh, what's that?
Wait, hey,
No questions here.
Acid to water, not water to acid.
it's a correction.
It is. No.
Because when you said put 1
Dallas,
and 2 in there,
Dallas. I need my thought, Dallas. Hold on. From 6 molar to 1 molar was negative 4484. joules per mole. From 2 molar to 1 molar, you said was negative 0.69 joules per mole.
Except that it wasn't, that number was just ln of 1/2.
Oh, give me the whole damn thing.
Negative 1717.
Okay, it still demonstrates my point. Negative 1717. I need to get this thought down, Dallas, because I've never done this thought with people before. Sorry. 1717. Okay. Notice the difference. This reminds me of a safety tip, and I believe Ben said it. Somebody said it.
Acid to water, not water to acid.
Yep. Because what are we doing? We're going from concentrated to less concentrated. You go from that 6 molar down to 1 molar, that's a lot of energy. You're going 2 to 1, right? God forbid you go from 12.1 down to just pure water. You're going from 12 molar down to, you name it, like 0.001. Holy cow. In fact, let's do it. Dallas, get it to me. Say, go from concentrated 12.1 molar HCl to 0.001 molar HCl.
I'm getting negative 23291.
Yeah. And it doesn't take much to get a mole of that stuff. And if you think about 4.186 joules per gram Celsius for the specific heat of water, that is a lot of energy being dumped into that water. You don't think it's going to flash boil and spray everything everywhere? Boom. Thank you guys. A mo thought I hadn't even looked for. Bringing it full circle all the way back down to Chem 120. Now, what I would like to do too, real quick, quick side thought. Delta G equals negative NFE. That's from the beginning of this. This is converting Gibbs to voltage. Rearrange this, it's negative delta G over NF. And for what we just did. I've never done this. I don't know if this is going to work. But our delta G up there was negative 4484 joules per mole. The number of electrons transferred is going to be 1. And Faraday's constant is going to be 96486 coulombs per moles of electrons. And I think it's only 1 electron, not 2. Yeah, I think it's just 1. Dallas, can you get me that number?
Negative 0.0465.
Oh, sorry. It was, we had a negative of a negative, so 0.0.
465.
Okay. If you're diluting from 6 molar to 1 molar, you get basically 0.05 volts. What I'm going to do, I wonder if there's a way to pause the recording. Is there a way to pause it? Do you know? Oh yeah, I can. I'm going to pause the recording real quick. Okay, so what I've done here, guys, is I ran back into my place, got myself a voltmeter, and hopefully you guys can see it reads 0 volts. I've got an open circuit here. I don't know how easy it is to see, but I have a pile of salt right here. I got myself actually some reverse osmosis water, so there should be no ions in it. And what I'm going to do is I'm going to pour it onto the salt here, get it nice and dissolved right there, make a nice little steady stream. I'm going to make a stream right here to connect it. And I'm going to put my leads in here. And we see a voltage. Now I have it switched. So to make the positive voltage, I'm just going to switch my leads. But you see a voltage there of 40 millivolts. You guys see that?
Yep.
Yeah. That's kind of cool. The more that salt is dissolving in this pile and trying to work, wick its way through to the other side where there's no salt, you get more voltage. But this will start to go down as my red one here starts getting more and more concentrated because there'll be less driving force to get it there. But there you go. You can get energy out of dilution. We just had to put some leads on it. So, and what did we say we should think about getting? 0.05, so 50 millivolts. Yeah, and we got basically 50 millivolts. That's kind of cool. At least I think so. All right, I'm going to go ahead and stop the recording.